mentioned that group delay is a function of the far field phase pattern. And so instead of just looking at the single point directly between the antennas, we're able to look at a couple of cut planes around the antenna. So here we've set up 2 planes for an observation angle. We have the H plane as well as the E plane. And if we pick just the point in the middle, so on the XY axis, theta equals 90 degrees, phi equals 0 degrees, we can take that data, and this gives us the antenna group delay that we looked at before. This is antenna group delay versus frequency. We can take the maximum value, the minimum value, it comes out to roughly 21 picoseconds. So this is the single data point for that observation angle. We can get the same, or we can go through the same process and get a single data point for all of these observation angles in the H plane as well as the E plane. We could plot those directly if we wanted, or instead we created a CDF of this, so a cumulative distribution function, just showing more of a statistical perspective of how does the group delay vary over the 2 planes. And so here where they intersect, that's the single point that is on both the E plane and the H plane, around 21 picoseconds. We wouldn't expect very much in the H plane, and we're seeing that here in the graph. Roughly it's 21 picoseconds. It's a vertical line. It doesn't matter which point on that plane we are at, we're getting the same 21 picosecond variation. If we look at the E plane has more variability in it. We're moving up and down closer to the poles, and the variation in group delay moves around, right? So sometimes it gets a little bit better. The variation decreases less than 10 picoseconds, and in a worst case, the variation for a single point would be around 28 or 29 picoseconds.